Welcome to section 10.3, where we're going to be comparing two independent population proportions. All right, so the requirements to do this type of hypothesis test is we need to have two independent samples that are both from simple random samples. The number of successes and failures is at least 5 for both of them, and the population must be 10 times the size of the sample for this hypothesis test to work appropriately. Comparing two proportions is a very common thing to do. The hypothesis test can determine if the difference between the two proportions is due to a difference in the population or if it's just due to chance. When we compare two independent population proportions, the difference of those two proportions is what we're going to be looking at, and it follows an approximate normal distribution. So the general setup for these types of problems are going to be that the null hypothesis is that the proportions are equal. Then we're going to set up a pooled proportion, which is sort of an average of the two, using this formula right here. Our pooled proportion, P sub C, is going to be equal to the number of successes in both groups divided by the number of failures in both groups. When we set it up this way, then our null hypothesis is that this population proportion follows the normal distribution. The difference follows the normal distribution with a mean of 0 and a standard deviation of this big, ugly mess right there. However, you don't really need to write this down. We're going to be using our our hypothesis calculator online. We'll go back over and talk about how this looked at the end. Let's do an example. Two types of medication for hives are being tested to determine if there is a difference in the proportion of adult patients' reactions. 20 out of a random sample of 200 were given medication A, and they still had hives 30 minutes after taking the medication. 12 out of another random sample of 200 adults given medication B still had hives 30 minutes after taking the medication. We want to test this at a 1% level of significance. First, let's notice that our number of successes and failures is over 5 for all of them. We have 20, successes and 180 failures in the first group, 12 successes and 188 failures in the second group. All right, step 1, as always, is find the null and alternative hypotheses. So we want to find out if one of the medications is working better than the other one. So our null hypothesis for these types of problems is always going to be that they're equal. So the proportion of A is equal to the proportion of B, or we can think of that as a difference, that the proportion of A minus the proportion of B is equal to 0. That means our alternative hypothesis is that they're not equal and that their difference is not equal. We're going to figure out what the appropriate distribution is and write down what we know. Well, we know the number of people in sample A and the number in sample B are equal to 200. The number of successes in A is 20 and the number of successes in B is 12. Our pooled proportion is 20 plus 12 over 200 plus 200, which equals 0.08. And if we fill all that in, that's going to be our distribution. Remember, we always use a normal distribution for proportions because we're talking about binomial. And when you have binomial with a large enough sample size, we're going to get to be approximately normal distribution. All right, so let's go ahead and plug this into our inference for the proportion calculator. We have two samples, and our alternative hypothesis is that they are not equal. We're going to put in some sample statistics information. We have 200 in both samples, and the number of successes in the first sample is 20, and the number of successes in the second sample was 12. Right, hit compute, and we got our results. Our test statistic has a value of 1.47. Our p-value is 0.14. p-hat1 is 0.1, and p-hat2 is 0.06. We were going to test this at a 1% significance level, so alpha is equal to 0.01, and this was a two-tailed test because the alternative hypothesis was not equal. So it could be really high or really low to be rejected. If we look at our p-value, it's higher than our alpha, right? P-value is 0.14 and alpha is 0.01. When the p-value is high, the null must fly, so that means we do not have enough evidence to reject the null hypothesis. Remember, on this one, as with all the proportion comparisons we're going to be doing, the null hypothesis is that the proportion of patients in both samples were equal. So we cannot conclude that there is a difference in adult patient reactions given medication A or given medication B. Step 5, this is just something I like to do. You don't have to do this on your homework if you don't want to, but it helps me a little bit to look at the picture. The difference between our two p-hats that we computed, the probability of the success proportion for medicine A and the success proportion for medicine B, was 0.1 minus 0.06, which is 0.04. So if we're looking at our normal distribution, and I plugged in the one we calculated here with all that value, we can see that 0.04 is right here. So above or below that guy has a probability of 0.07 to be above it and 0.07 to be below negative 0.04. We add those guys together, that's where we get the 0.14 probability that we got it for our p-value. Remember, our p-value is 0.01, so those probabilities are not high enough to reject this hypothesis. All right, that's it for this section. Short video today.